Okay, so today we're talking about equations of sinusoidal functions. All right, so this is 8.4, and remember we talked about this term sinusoidal, right? It's any graph that has the shape of a sine graph. So it could be sine or cos or any variation of. Now, variations of sine and cos graphs come when we change the parameters of the graph. Okay? So as you can see here in your textbook, y equals 3 sine x plus 2. We've changed some parameters. This is not just a simple y equals sine x, right? Because we know from 8.3 some characteristics of the sine graph, right? It starts at 0, it goes up to 1, it goes back down to 0 at 180 or pi radians, then it goes back down to -1, then it comes back up to 0 at 2 pi. So we know lots of things about the sine graph. But now how do these numbers here and others that we'll find that we can place inside this equation, how does that change the shape of the graph and where it is and stuff like that? So that's what we're studying today. So if we go back to the notes here, equations of sinusoidal functions. So as I mentioned, there are some parameters that we're going to study. And in pre-calculus 30, the other 30 level math class that some of you might have taken, I'm not sure if some of you have or not, but there's a lot of study on transformations, and that's what this is. You take a graph, you stretch it, or you compress it, and you move it up, or you move it down, or whatever. You transform the graph. And so that's a little bit of what we're getting into here today. So this looks a little funny, but these are all the parameters that we're going to study for the changing of something that looks like a sine graph. So we have y equals, and I'll get you to write this down. So here's the regular sine graph, right? Y equals just sine x. Well, we're going to figure out what happens when we change the number that multiplies to the sine. We're going to figure out what happens if we multiply something by the x, and what happens if we have a constant that's either added or subtracted here, and then what about a constant outside of the sine brackets there. So we're going to figure out all of those today, and you're going to see, and I'm going to show you what's going to happen when we change those. Okay, so with your graphic calculator, you can follow along here what I'm doing on the screen. I am actually going to show you, first of all, we're going to take a look at A, and what does A do to the regular old sine graph. So I'm going to pop over here to Desmos here now. And the first one, the red graph that I have here, this is a sine graph. Okay? It is a regular old y equals sine x graph. Now I'm also going to light up this next one, which is y equals A times sine x, and I've got A on a bit of a slider here, so I can change the values of A, and you're going to see that when I change the value for A, right now it's 1, so it's the exact same as just y equals sine x. It's y equals 1 times sine x. But if I make A larger, watch what happens. So the blue graph is now, right now, it's y equals 2 sine x. So what parameter has changed? The what? Thank you, amplitude. Very good. That's exactly what I was looking for. Okay, so we remember those terms. Amplitude is sort of the distance from the midline to the maximum point or to the minimum point, right? Okay, so that's very, very good. Now, if this A goes higher and higher, the amplitude goes higher and higher as well. So there you go. So that's how it changes. Now, if we take A less than 1, okay, it kind of squashes down, right? So if A is between 0 and 1, we have a smaller amplitude, and the amplitude matches the A value. Okay? So A, amplitude, okay, easy to remember. If A is negative, watch what happens to the blue graph if A is negative. I'm going to go down here. If A is 0, we have just y equals 0, because 0 times sine x is 0. And then negative, look at that, it kind of flips around, you see? So that's -1 there. Cool, eh? So the absolute value is the fancy term for just the number portion, not the sign, positive or negative. So the absolute value of A causes the amplitude to change, okay? So there you go. That's A. Awesome. Okay, let's go back to A equals 1, or I can just maybe deselect that one. So let's just jot down what we learned here about A. So A what? A is the, actually the absolute value of A would be the amplitude. So A, it's what it's called is a vertical stretch. Vertical stretch, which is basically the amplitude. Okay. So if a is greater than 1, and I don't like this blue color, this is the wrong one. If a is greater than 1, then it is stretched up vertically. So increased amplitude stretched vertically. So stretched up, stretched, yeah. Do I want to say up? I'll just say stretched vertically. Okay. And if a is between 0 and 1, okay, I'm going to say it's compressed vertically. Okay? I just like to use those terms because a stretch, you know, is pulling apart, right? It's pulling up, it's stretching it up. And a compression is like a squeezing down. So those are the terms I like to use, and that might help you remember. Okay? So a is the vertical stretch. The absolute value of a is the amplitude. Okay. Okay? Any questions about a? So that is a. We've got that kind of figured out there. Now, b. I guess, you know, yeah, we'll do b next. B is a little complicated. I think b is probably the toughest one, actually. The toughest one to keep track of what this actually does to the graph. So a is a vertical stretch. B, let's see what happens when we change b. Okay, so here is y equals sine of bx, okay, the purple one here. And right now I've got b equals 1. So sine of 1 times x is the same as sine of x, right? So if I change b, watch what happens. I'm going to increase b. Look at that. It kind of squishes it up horizontally, doesn't it? So this is a b value of 4 right here. So you take a regular old sine graph like this and you squish it up. That's what happens. The b value, if it gets larger, it squishes it up. Here's another way to think of the b value, and this might be a little easier if b is 2 here. Okay? So if b is exactly 2, there we go. It's exactly 2. This is one way you can think about this. The red graph is sine, right? It's just regular old sine. And the period is 6.28 radians, or 2 pi radians. Look at this. We now have, instead of 1 sine graph, we now have 2 sine graphs. So when b is 2, it's kind of like where 1 sine graph would fit, now 2 sine graphs fit. Okay? So you can think of b as how many regular sine graphs would fit in 2 pi. The other thing you could do is, well, it's a compression of 1 over whatever that b value is. So if b is 2, it actually is compressing it by a half. Or the period length is now a half of what a normal sine is. Okay? So let's do that again. So here's 1. There's 1. And if it goes up, it starts to compress. See, 1.5. Look at, there is 1 sine graph and then 0.5. Okay, within that 2 pi span now. Or you can say the graph has been compressed 1 over 1.5. That's 2/3, right? Okay, so let's just jot this down to b there. So b is the horizontal stretch. Okay, so 1 over b, okay, 1 over b is equals to, or it refers to the stretch, okay, or the compression. So stretch, or if we're using those terms, compression. Another way to think of b, so these are all different ways to think of and understand b. So b, this is also the number of sine graphs to fit inside 2 pi. So if it's compressed, by a half, that means you can fit 2 in there now, right? Okay, so the period length, here's another thing. Period length equals 2 pi divided by b. 2 pi divided by b. So if I have a b of 2, right, that means 2 sine graphs can fit into 2 pi. Or the period length of 1 would be 2 pi divided by 2, or 1 pi. So the period length of 1 would be 1 pi instead of 2 pi. See that? So hopefully this is all kind of fitting together for you. But B, like I say, B is a little bit, that's the trickiest one I think to figure out. Now I'm going to throw one more thing there on you. Okay, one more thing now. Remember how we talked about absolute value here on amplitude? The negative and positive doesn't really have anything to do with the length of the graph. It has something else to do. It's like it actually flips the graph, which we're not going to get into right now. But technically, this is absolute value, and I think you might see this in your text. So I'm going to do this now. Okay, I don't want to freak you out at the beginning there. But it's the absolute value of b, so the negative kind of says something different. But the actual b value talks about the period length. Okay? And to tell you the truth, because I teach pre-calculus as well, I'm not really sure if they're getting into the negatives for you guys here or not. To tell you the truth, I don't even know. We'll see if we come to it, okay? But we won't worry about the negatives right now for A or B. Okay, so A, easy, right? Vertical stretch if it's greater than 1. Vertical compression if it's between 0 and 1. B, if B is greater than 1, that means it's a squish, a compression. If B is between 0 and 1, did I show you that? Yeah, I think I did. If B is between 0 and 1, that actually means we have a horizontal stretch. So there we go. See how the blue graph or purple, whatever that color that is now stretched out. You see? There's one period up to there. 0.6. Okay? Questions about B? A vertical, B horizontal. All right. How can you remember that? B is with the X. B is right with the X there. So that's X is this way. X. Okay? That's another way to remember that. Okay, so C and D now. Let's talk about C and D. Okay. So here I've lit up now, this is green now. Y equals sine of X minus C. So the pattern is minus, okay? And I'll get into that in a second. But if I subtract 0 from X, I still just have X. So when C is 0, or maybe I'll move that up a bit. When C is 0, X minus C is just X, right? What happens if I make C larger? Any ideas what's going to happen? Sorry? It's going to go that way. It's going to go that way? What do you mean? Like, okay, so it's going to, when you say go, what do you mean by go? It's going to translate, it's going to move. Okay, let's see. So here's, whoops, that's D. Why am I doing that? That's the wrong one. 0, please. Thank you. Okay, C. Look at that. If you move C, that moves the graph left or right? Left or right? Now, if C is positive, so here's, where's 0? There's 0. If C is positive value, it moves it to the right. But here's what's important. It actually shows up in the equation as a minus C. So it's sine of X minus 2.5. Actually moves that graph 2.5 units to the right. Okay? So you'll get the hang of it. But yeah, C is a horizontal translation or a horizontal shift. Okay? Now, I've got the notes already written out for C and D. Okay, so I'm just going to walk through this slowly as you copy this out. Okay? So C is a horizontal translation, or another word for translation, might be a shift. So just a movement, left or right. It doesn't stretch it, it just moves it left or right. So the shape does not change. It's just the position of the wave, or of the graph. Okay? So because, as I mentioned, the format is X minus C, if you had something like sine of x minus 90, where this minus 90 is inside the brackets with the x. That means it's a movement along the x-axis, or that way, horizontally. That actually means a 90-degree shift to the right. Okay? So it's kind of like the opposite sign of what you see there. Okay? So C is kind of, you move it the opposite way from what it looks like you should. Because negative, right? Negative looks like it should shift left. That's where all the negative numbers are. But if it's a minus C, it's actually shifting to the right. Okay? And then the other piece to that, of course, is if you see an x plus something, that means it's that something to the left. It moves it to the left. So this is kind of opposite world here when you look at the signs, okay? All right. So A, B, C. Right? Just need that to music. Okay. All right, so let's see what D is. Finally, D. Now this is going to be easy. D is going to be easy. Okay, so D, look at this. D is outside of the sine function. A is multiplied by the sine. B is multiplied by the x. C is inside the sine again with the x. D is totally outside. So if I move, let's light this up here now. So if I add 0 to sine x, it's still 0. But if I add something to the sine x, check it out. Look at that. It moves the whole thing up or moves the whole thing down. What was that? It's like teeth, yeah. Yeah, it's kind of like a smile or like teeth or something. Braces on. Okay, so D, let's go back to the notes. D, there's the B notes apparently. Okay, so D is here in red. Vertical translation. D. Vertical translation. So remember, translation is a move. Stretch would be a stretch. Translation is just a move to translate. So think about translating language. Just move from one language to the other language. Just a move. You're not distorting the words at all. You're just trying to move. So translation. The graph moves D units up, if it's of course positive, and D units down if it's negative, or if it's a minus. So that one's pretty straightforward. It's not opposite world like the C. Okay? D is a vertical translation. Okay, so guys, here's the last thing I'll show you now. So if we put this all together, and before I start, I want you to notice something. Okay, girls, this is very important. Inside the sine function. Now remember, sin, the sine, or cos, cosine, or tan, tangent, whatever it is, that's not an entity unto itself. Okay, that's not. We're not like multiplying sine times something else. It's not times. It's all part of the function. So that sine needs an x, or needs a number, needs something in there to go together with it. There, it's connected. So inside here, though, this is b. And then there's actually a set of brackets around x minus c, okay? And that's actually going to be pretty important. So just make sure that you know that it's not bx minus c, it's b bracket x minus c, okay? So in order for this c to move exactly the way we've predicted, there cannot be a number in front of the x here within this bracket, okay? And we'll talk maybe more about that as we go. But that's kind of, I just want to outline that. All right, so now if I move D, we know that this is going to move up, down. Okay, so let's have D there at about 1.8. What about C? If I move C, I'm going to move it left to right. Okay, so there we go. Let's put the C there. B is a stretch. So look what happens here. I'm going to compress it a little bit because I'm going to up the B. And A, I'm also going to stretch that in the vertical direction. And so there we go. There we are. So this is the graph in the purple there, blue, whatever color that is. I still can't figure that out. This is the equation for y equals 4.7 times sine of 2.1 bracket x minus 2.2 bracket plus 1.8. Okay, plus 1.8. So there you go. So if you put them all together, you can get any kind of sinusoidal function you want, any kind. And so all of these parameters contribute to a sine-like graph that you can basically put in any shape you want. You can put it anywhere. You can move it up, down. You can stretch it, right? So all this stuff can happen here now. So there you go. You can make all sorts of funny designs and stuff like that. But most importantly, if you have a situation like the Ferris wheel one, or like a wave in the ocean, or a particle moving up and down over time, you can manipulate or change the parameters of a sine function, and you can model exactly that motion if it's a periodic predictable motion, right? So that's the important thing. We can change the parameters to basically mimic any sort of periodic situation in life like that. Okay? All right, so let's just finish off with one more thing here. We're going to take a peek at a graph here, and I want you to help me figure out what the A, B, C, and D what they are. Okay? So A, take a look at this graph up here. I think you might have it in your textbook somewhere, I'm not sure. Hopefully the answers aren't staring you in the face, but anyways, don't find it. So let's just take a look at this up here. What is the A value? And remember, A is amplitude. So from the middle to the maximum point. Or it's half of the maximum to the minimum. So what is A? It's a little tough to maybe see exactly where the midline is here. So let's take a look at this. This is -3, and this is 5. So what's that a total of? It's 8. So A is 4. And here would be the midline if you add 4 to -3. So A is 4. You see that? That's how you now can look at a graph and decide what the parameters are. Good? Okay, B. Oof. B is a tough one. We have to find out what the period is. That's how we find out what B is. So 90 to, what is that? Each of these are what, 30, 60, 30? So that's 210, is it? Okay, so remember for B, the period length is 2 pi over B, right? Absolute value, but we won't worry about that right now. So how do we find out what B is? Well, we look at what the period length is, and then we can solve for B. So the period length is what? What's this distance here? It's 30, 60, 90, 120. Does that make sense? So this is 120 degrees. Now, got an issue. This is radians. Period length is in degrees. What do I do there? Can I have radians and degrees in the same equation? Say no, say no. No. So how can I change this to match up with degrees? What should I change? What should I change? Thank you. 2 pi. Wow, you're quick. Okay, so I'm going to make that what? 360 over B. The period length is 120 degrees. See? You can solve for B. So B is, 360 over 120. What's that? 3? Okay. That's a 3, and it's a 6. So you guys with me there? Okay, remember this is important. Period length is 2 pi over B, or 360 over B. Okay. All right, so that's B. We got B equals 3, A equals 4, B equals 3. Now what about C? Okay. So this is where it gets maybe a little bit tricky. If we're talking about a sine graph, what you kind of have to do is you kind of have to start at 0 here and try to find where the beginning of a sine graph would be. So where is the nearest beginning to a sine graph? Well, this is an upside down sine graph, but this wouldn't even be the beginning here, would it? Because that's not a sine graph. So that doesn't work. Where's the beginning of the sine graph? So first of all, we have to find that midline, which we said was 1. So here's the midline, and look at this. This would mark the beginning of a sine graph, and there's the end. You see that? So do you see how inside that wave there is a sine looking graph? See that? So what this means is that 0 would be where it normally should start. It should start here at 0, 0. But it's actually been shifted this way. How many degrees? 60. Yeah, 30, 60. So it's gone 60 degrees this way. Okay? So now C could be an infinite number of different numbers. Because there's a beginning here, there's a beginning here, there's a beginning here, there's a beginning back in the negative. But you only need to pick one. And so what we want to do probably is pick the one that's close to 0 and one that maybe is positive, but doesn't matter. So what I'm saying is that this is one option for your C value. This is probably the easiest one to find. So C is actually 60 degrees. Because you see it's shifted from 0, it's shifted over 60 degrees. That's the new starting point for the sine graph. Okay? Now the other thing is, obviously this sine graph has been moved up as well to have the starting point here. So the starting point should be at 0, 0 for a regular sine graph, but it's moved to the right 60 and it's moved up how many units? 1. So what is D? 1. It's been moved up 1. So D is 1, positive 1. Okay? Now that may take some practice, all right? This may take some practice. I don't mean to go too fast here, but I think many of you are nodding your heads and kind of putting this together now. So you can identify A, B, C, and D from the graph, and that's how you do that. So finally, what you would want to do at the end here is to put all of these parameters into this sine format. And so A we said was, what did we say it was? Where is it? Up there? 4. So you have a 4 here times sine of, what's B? 3. Okay. Okay, so 3 for B, and then C is 60, so it's going to be X. It's 60 to the right, so that's X minus 60. And then D is 1, so that's going to be up 1, that's a plus 1. So that's where those values go, and you have sine y equals 4, sine of 3, x minus 60, plus 1. And that is the equation of this graph. And if we put those values into your graphing calculator, you should have this graph, exact graph, show up. Okay? I haven't looked at my notes at all, so hopefully that's right. I don't think I made any mistakes, but... Okay, any questions? No? Grade 12s, just as you get started on your homework assignment, could I have your attention just real quick? Girls? So, the in summary, okay? Take a look at the in summary here. Again, this is a summary of what we've done. If there's anything in there that you don't understand or think that I haven't talked about that you want to ask questions about, you can certainly let me know. But this should be everything in here that we have talked about. We didn't really do an equation for D, right? But there's how you would calculate D. Okay, maximum plus minimum divided by 2. That's the average. That's really the equation of the midline, isn't it? So that's what D is as well. So anyways, you can look at that as well.